Welcome back to Calculus 2. I'm Dr. Jeff Grove. Today we're going to talk about the method of partial fractions. The good news is you learned about partial fractions in pre-calculus, so you already have a fair amount of knowledge about this procedure. We're just going to throw in integrals. In fact, this is not really an integration technique so much as it is an algebraic technique designed to split rational functions into simpler pieces. What is a rational function? A rational function is a function that may be expressed as the ratio of two polynomials. A polynomial divided by a polynomial. You can immediately recognize when the method of partial fractions should apply if the integrand is a rational function. I want to introduce this method using examples. Suppose I'm integrating 2x divided by x squared plus 5x plus 6 dx. How do I integrate this? The derivative of the denominator is 2x plus 5. We have the 2x, but we don't have the plus 5. What we'll do is we'll split this complicated fraction into simpler fractions using a purely algebraic method. I'll start by ignoring the integral. I'm not going to write equal because what I'm writing is not equal to what is above. It's a little side computation. I'll separate it from the rest. I'm going to factor the denominator. The denominator factors as x plus 2, x plus 3. And the trick is to try to divide this into little terms, separate terms. One term with the denominator of x plus 2, and another term with the denominator of x plus 3. We don't know at the outset what the numerator should be, so we're just going to denote them by letters, a and b. We'll try to figure out what a and b have to be. If we can split this complicated fraction into these two simpler fractions, these will be a lot easier to integrate. If there really do exist constants a and b, so that this fraction can be separated into these two pieces, then we should be able to get the same equality to hold if we clear the fractions. We can do that by multiplying both sides by the denominator on the left-hand side. On the left, those factors all cancel. On the right, we'll distribute the whole thing to each term. We'll have 2x is equal to, on the first term, x minus 2 cancels, leaving us with a times the quantity x plus 3. On the second term, it's the x plus 3 that cancels, leaving us with b times x plus 2. At this point, this equation must hold for all replacements of the variable, for all x, which means it holds for any x that we choose. And there are strategic choices for x, say x equals minus 2, that will help us figure out what a and b have to be. If x is equal to minus 2, we'll get negative 4 equals, well, negative 2 plus 3 is 1. That gives us a. A is negative 4. Can you think of another reasonable choice for x? I hope you thought of negative 3. There we get negative 6 equals, the first term will drop. Negative 3 plus 2 is negative 1 times b. We get b is equal to 6. We can put these together now and figure out the integral. Our integral will be negative 4 over x plus 2, and then plus the integral of 6 over x plus 3. Those are easy. The derivative of x is 1. We can move the negative 4 out and have this in the form f prime over f. Same thing over here. Move the 6 out, leave a 1 up top. It's now in the form f prime over f. It's easy to integrate. Our answer is negative 4 times the natural log of the absolute value of x plus 2 plus 6 times the natural log of the absolute value of x plus 3, and don't forget that constant of integration. The last problem was particularly simple because the denominator factored as linear factors to the power of 1. Let's try something a little different. Let's suppose that we have, say, 5 over x minus 3 squared times x squared plus 4x plus, let's say, 13. And we're integrating. How do we integrate this rational function? Power 2 here is a giveaway that we're going to rewrite the integrand as 5 over x minus 3 quantity squared, x squared plus 4x plus 13, and rewrite that as a over x minus 3 plus b over x minus 3 squared. Remember, if you have a multiplicity greater than 1, then you have to start at 1 and work your way up to that multiplicity for the root of the denominator. The quadratic that's left does not factor over the real numbers. In this case, we call this an irreducible quadratic. Whenever you have an irreducible quadratic, there is a certain thing you need to remember. The numerator, if you can't factor that quadratic over the real numbers, the numerator must be linear. So we are going to have cx plus d in the numerator of this last term, which has a denominator of x squared plus 4x plus 13. One way to determine whether or not this last factor is an irreducible quadratic is to check the discriminant of the quadratic formula, b squared minus 4ac. In this case, we get 16 minus 4 times 13. This is definitely negative, which means the roots are complex. It does not factor over the real numbers. To proceed with the method of partial fractions, we need to clear all of the denominators. We need to multiply both sides by the denominator of the left-hand side. On the left-hand side, we will get 5. On the right-hand side, we have to distribute this denominator to each and every single term. Make sure you get the parentheses right, too. On the first term, an x minus 3 will cancel, leaving us with a times x minus 3 times x squared plus 4x plus 13. On the next term, both factors of x minus 3 cancel, leaving us with b times x squared plus 4x plus 13. On the last part, it's the quantity cx plus d. Don't forget the parentheses. It's important. It's part of the order of operations agreement. The x squared plus 4x plus 3 cancels, leaving us with x minus 3 quantity squared. At this point, there are two ways that we can proceed. You can either plug in strategic choices for x, or you may equate powers of x on each side of the equation. That would require multiplying through by everything in sight. We already used the method where we chose strategic values of x. That's not going to work very well here because when we choose x equals 3, that will give us b. The only other easy choice is x equals 0, and that gives you an equation involving a and d. It won't solve for anything. It looks like there aren't a lot of other good options for choices for x. So let's pursue the second method, the method where we equate powers of x on each side of the equation. The highest power of x that will appear is a cube. So you're going to have x cubed. There's going to be an ax cubed. There will not be a bx cubed. We'll square this out, giving us x squared minus 6x plus 9. When we multiply, we will get a cx cubed. The next highest power will be squares. We will get when we FOIL out the x minus 3 times x squared plus 4x plus 13, we'll get a 4x squared minus 3x squared, which is 1x squared, times a. We will get a bx squared. And then, as far as the c's are concerned, we'll get a negative 6c, but we'll also get d, x squared. Now, what are the x terms? We'll get a 13x minus 12x, that's 1x, times a, plus 4b. We'll get a 9c, and we'll get a minus 6d. And now the constant terms. We'll get negative 39a plus 13b, and then plus 9d. We need to equate the coefficients on both sides of the equation. The coefficient of x cubed on the left is 0, and on the right, a plus c. So a plus c is 0. Same thing with the coefficient of x squared. A plus b minus 6c plus d is 0. Same thing with the coefficient of x. A plus 4b plus 9c minus 6d is 0, and one more equation. Negative 39a plus 13b plus 9d is equal to 5. We have 4 equations in 4 unknowns, a, b, c, and d. We should be able to solve for the unknowns. My calculator tells me that a is negative 25 over 578. B is 5 over 34. C is 25 over 578. And D is 45 over 289. Now for our integrals. Our integral, which I'll denote by I, is negative 25 over 578 of, let's see, we had x minus 3 plus b over, let's see, b is 5 over 34, the integral of 1 over x minus 3 squared, and then the c and d parts. C is 25 over 578 x plus d, which is 45 over 289. This is all over x squared plus 4x plus 13. The first two are not difficult to integrate. We'll get the log of the absolute value of x minus 3. On the second term, we should write that as x minus 3 to the minus 2. That way we'll get 5/34. We'll have x minus 3 to the power of negative 1 divided by -1. Now, for the last part, it takes a little more work. Notice that 2 times 289 is 578. I'm going to factor out 1 divided by 578. What's in top now is 25x plus 90. In the denominator, I'm going to complete this square. X squared plus 4x plus, if I want to complete the square, I need 4. Well, 4 plus 9, I'll have x plus 2 quantity squared plus 9. And what's left? I wish the numerator of this last integral was 2 times the quantity x plus 2, which unfortunately is not what I have. But I get what I want. I'll just need to pay for it. So, how do I get 2 times the quantity x plus 2? Well, here's how you do that. First, I'm going to rewrite this. We'll have minus 5/34 times 1 over x minus 3 plus 1 over 578. Now, on my integral, I'm going to factor a 25 out. Now, for the numerator of the integral, I'm going to write this as 25 times the quantity, x plus 2. Well, I'll get 25x plus 50, not plus 90. So I still need to add plus 40. I'll break this now into 2 integrals. We'll have negative 25 over 578 times the natural log of the absolute value of x minus 3 minus 5/34 times 1 over x minus 3 plus 1 over 578 times 2 different integrals. The first one is 25 times the integral of x plus 2 over x plus 2 squared plus 9 dx. And the last one is plus 40 times the integral of 1 over x plus 2 quantity squared plus 9 dx. Now, I really wish I had a 2 here. I'll put a 2 there and pay for it with a 1/2 out front. On the other term, it's going to take a little more work. On this first term, first integral, we're set up for log absolute value of the denominator, f prime over f. The last one does take a little more work. Here's what we'll do. We'll set the square root of the variable stuff, x plus 2, to be the square root of the constant 3 times a new variable u. In this case, dx is 3 du. Let's see how that transforms that last integral. We'll have minus 25/578 log absolute value of x minus 3 minus 5/34 times the quantity 1 over x minus 3. Now, we can distribute, I suppose, 25 over 1,156. On this last part, we're going to get log absolute value x plus 2 squared plus 9. And I guess technically the absolute values are superfluous here. Continuing to distribute, I guess we can cancel a 2 here. We'll get 20 over 289, the integral. Well, let's see. X plus 2 gets replaced by 3u, so we'll have 9u squared plus 9 in the bottom, we'll factor the 9 out. And on the top, 3 du. We get a little bit of cancellation, and then it looks like we have the 1. We'll have 600 plus 240, that's 840, plus 27 is 867. And it's arctangent, because the integral of 1 over u squared plus 1 is arctangent of u. But u is x plus 2 over 3 plus c. Okay, so I really introduced 2 new aspects of the method of partial fractions here. The first one was the repeated root, and how you have to separate that out into a over x minus 3 plus b over x minus 3 squared. You go all the way up to the highest power that appears in the denominator of the original rational expression. Also, if you have an irreducible quadratic, you have to have a linear numerator, so we used cx plus d in this case over that irreducible quadratic. I now want to move on to other strategies. Let's suppose you encounter an indefinite integral and you have no idea how to find the antiderivative. In fact, it is entirely possible that the antiderivative may not be expressible with a finite number of additions, subtractions, multiplications, divisions, exponents, roots, logs, trigonometric functions, inverse trigonometric functions. It may be impossible to express it in a finite number of those terms, in which case we say that the integrand has no elementary antiderivative. In these cases, there is nothing you can do except invent special functions, which they do. I'll show you about that in a minute. Let me give you some examples. E to the x squared, the integral of e to the minus x squared, the integral of sine x over x, the integral of, say, cosine of x squared, the integral of the sine of x squared. These all have no elementary antiderivative, meaning it is not really possible for you to write down in a finite number of terms what the antiderivative is, unless you invent what are called special functions. Another strategy is to use tables. You can look up integrals in integral tables, and we have tables in the back of the book for these integrals. Let's suppose that you have a hard time figuring out the table. Another strategy is to use a computer algebra system. I'll show you one of those in a minute. But one last strategy. If you're dealing with a definite integral, then there are numerical approximation schemes. We'll talk about that in our next lecture. Let me show you an example. Let's suppose that I'm integrating 1 over x times the square root of 3x minus 5 dx. There happens to be a number in the table
It's number 88. Look up number 88 in the table on the back of your book. It says that if I have the integral of 1 over x, the square root of ax minus b dx, then what I get is exactly 2 over the square root of b times the inverse tangent of the square root of ax minus b over b, plus a constant of integration. It follows, therefore, that our answer is exactly 2 over the square root of 5 times the arctangent of the square root of 3x minus 5 over 5, and then plus c. Easy as that. Now, you need to be very careful with these tables because there are other examples in the table that are very similar, like number 89, but doesn't work in this particular case. Be very careful with that.
I'd like to show you a computer algebra system. Let's integrate the exact same problem we just integrated. 1 over the square root of x times the square root of 3 times x minus 5. With respect to x, there. What do you get? There it is. Notice that the computer algebra system does not have the constant of integration. It leaves those off. In that way, it makes it maybe easier to manipulate these expressions that you get from these integrals in more complicated programs. But what do you get if you integrate something like the square root of x squared plus 6 times x with respect to x? You can see this gives us these antiderivatives very quickly, very efficiently. Suppose I'm integrating 1 divided by 1 plus the sine of x as x goes from 0 to pi. Notice the capital P on the pi in Maple. This is Maple that I'm using here. It gives me the answer, lickety split. Could you do any faster? Suppose I'm integrating 1 divided by the square root of exp of x plus 1. exp of x is the exponential function e to the power of x. That's how you express that in Maple. And it gives me negative 2 times the arctangent, inverse hyperbolic tangent of the square root of e to the x plus 1. Isn't this truly phenomenal? But I want you to see some others. Suppose I'm integrating exp of x squared. We just said this has no elementary antiderivative. In fact, it gives me negative 1/2 the imaginary unit I. That's how Maple expresses the imaginary unit. Instead of a lowercase I, it uses an uppercase I. The square root of pi, ERF. Do you know what ERF is? Of I times x. ERF is something called the error function. The error function has a special name, ERF. We can look this up. Topic search, ERF. It tells me exactly what the error function is down here in the middle of the page. ERF is 2 divided by the square root of pi times the integral of e to the power of negative t squared as t goes from 0 to x. This is very much related to the normal curve, a normal distribution, and it's finding the area under that curve from 0 to x. In fact, the 2 here can be replaced by 1, and you'll integrate from negative x to x. It gives you the area under the normal curve between negative x and x for any value of x that you choose. This is how you calculate these normal probabilities. Since there is no elementary antiderivative, you have to do it numerically, and Maple calculates these
numerically. As easy as that. So, yep, we get an ERF function here. What if I'm integrating sine of x divided by x? This is another one of those that has no elementary antiderivative. It gives me a special function called SI. Let's look it up in the help feature here. Topic search, SI. SI, there's also CI and SSI, SHI, CHI. You can see that SI, the sine integral, is the integral of sine of t divided by t as t goes from 0 to x. These are all special functions because the integrand has no elementary antiderivative. Let's suppose I'm integrating ln of x. Oh, it's giving me EI. What is EI? Yep, these exponential integrals. Exponential integrals. The integral of e to the negative xt over t to the n. T goes from 1 to infinity. N is a non-negative integer, basically a whole number. So you can see we can use these computer algebra systems. It will spit out these special functions when you're least expecting them sometimes. When that happens, you know that you're dealing with an integrand that has no elementary antiderivative. The antiderivative must be expressed in terms of these special functions, as you've seen here. There are some others that I would like to look at. You know the 1 divided by x squared plus 1. Before I hit enter, you should know what the answer is. Arctan of x. If I'm integrating 1 divided by the square root of 1 minus x squared, that's the other one. You should know what that one is too. Arcsine of x. If I'm integrating 1 divided by x squared minus 4 times x and then plus 7, this has a very unusual denominator. You can complete the square, get x minus 2 quantity squared plus 3. It's an irreducible quadratic. You get complex roots. When that happens, you are going to get an inverse tangent, as you can see here.